So in today's video, I'm going to give just kind of an introduction to Monte Carlo and kind of random walks in two dimensions. And this is really to help you with your homework and kind of how to set up the problem and how to think about the problem. So we're going to use three libraries. We're going to use NumPy, we're going to use Matplotlib, and then we're also going to use this random int function from the NumPy random library. And recall randint will give us a random integer, which we can specify the range with equal probability. So let's start out. Imagine we have a particle and the position of the particle, initially the x position is 0 and the y position is 0. And I'm just going to plot it up. And the rest of this code is just kind of an ugly mess to kind of get a grid for my plot, a square grid. And here's my point at 0. So the idea in a random walk is the particle can move up 1 unit, right 1 unit, down 1 unit, or left 1 unit with equal probability. And so the easiest way to do this is we could just use the random int function. So we can say move is equal to rand int of 4. And what this is going to do is return an integer value where move is equal to 0, 1, 2, or 3. Right? And if you want to see this, we can just type print move. And in this case, you're going to see it's 1. And if I run it again, we're going to get the value 3. And I keep on running. I'm going to get some number between 0, 1, 2, or 3. And so now with those integer values, I can make assignments. And the easiest way to do this is with an if statement. So maybe if I say if move is equal to 0, let's move up. And if I'm going to move up, what I'm going to say is that p of y, I'm going to increment it by one value. So p of y is initially 0. I'm going to make it 1. So I'm going to set it equal to 1 or increment it by one value, and it's going to move up 1. Likewise, if I do elif and if I do move is equal to 1, maybe I'll assign that to down, and then I'll say p of y is minus equal to 1. And the next one, if I say move is equal to 2, maybe we can go right. And so here we're going to do p of x is equal to 1. So I'm going to increment the x value by 1. And then finally, elif move is equal to 3. I can move left. And then in this case, p of y, we're just going to de-increment it. And then what I want to do is just print up the new position of the particle. And let's do a blue color just to show the movement of the particle. And I run it. And so initially we're here at the center, and then we moved right. 1 probability. And if I run it again, now I've moved left. And then I run it again, and I move left, and so on. And if you want to run this a bunch of times, I can take this block of code. And then maybe I can do for I in range of 20, and I can look at 20 moves. And you're going to see basically it starts 0 and it's kind of moving all around in a random walk. And maybe if I do 200, you're going to see it kind of run off. And eventually it's probably going to run off the 10 by 10 grid that I'm showing because I've limited it intentionally here. And if I want to look at the final position, I can do p of x, p of y. And you're going to see it's 1, 19. In this case, it's still in the domain. But if I run it again, maybe it'll go off into some value. So 5, 21. So we'd be minus 5. And then 21 would actually be up here. Minus 5, 21. It's kind of rounding off kind of up here if I extend it off the graph. So that would be the idea of doing kind of a random walk. But maybe the next thing I want to do is maybe I want to bound this. So once a position gets to the 10 position, if it wants to move right, maybe it just gets stuck and it can't move. So it just doesn't move in case it's right. Likewise, if it's over here at the minus 10 position, wants to move left, that's kind of what its range to move is. We just assume it just gets stuck there. Likewise here and here. And so we're going to kind of bound it within this box. And this is pretty easy. All we're going to do is say if we have move here of 0, I can say if p of y is less than 10, my bounding box, then I'll increment it. But if not, I'm going to do nothing. And likewise, if I'm going to go down, I could say if p of y is bigger than minus 10, then I'll de-increment it, but otherwise I won't. Likewise here, if f p of x is less than 10, right, it's still in the box, I can move, but if it's bigger than that, I don't do anything. And then finally, if p of x is bigger than minus 10, I get px minus 1. And so now I run it, and you see it's basically forcing everything to stay in the box. And if I really kind of ran this out to 2000. It's going to take a second. This is one of the limitations of Monte Carlo. Final position, you kind of see it's kind of stuck in the box. It's kind of bounding off and eventually filling up all the points in it. Another way to do this is I could just not show every intermediate point. I could just show the final point. So after 2000 steps, we initially started here. We're diffusing around, and then we wind up here with it. There's lots of different ways to show this. So maybe we can also do something rather than doing this kind of looping the plots. Maybe I'll just do data is equal to px. Actually, I'm going to do data x, and I'm going to set that is equal to array of p of x, and data y is equal to array of p of y. And then what I can do, not the best variables, data x, I could append p of x here, and data y, I'm going to append the value of p of y. And then what I can do is plot up the positions, right? And so I could do like, data x, data y, and now it's connected, right? And then I'm going to just do 20 so it doesn't get too messy. And you're going to see kind of the connections kind of moving around. I can run it again. Actually, let me show the first point. And so I'm going to do plt plot. I'm going to do p. I'm just going to do 0, 0, put a line there. And actually, color is equal to red. And then line width is equal to 3. And we see a red point, and now we can kind of follow it. So it's kind of going down here, looks around here. I don't know, maybe it's looping up around here and following the trajectory in the diffusion. And obviously, if I do 200 points with the Monte Carlo, it's starting here and then it's kind of diffusing off. It gets stuck in the boundary because we have these boundary conditions here. And we can come back and run this condition. So one of the things we might ask is, I'm going to get rid of this data thing, is, so imaginally we're initially at 0, right? And then let me plot this up again. So I'm going to do this plt plot. P of x, p of y, put a circle here, and then a line width is equal to 3, and then color is equal to red. On this code. And so we're initially here. And then we can ask, we know it's going to diffuse away, and we can ask how long does it take to actually return to where it initially started. And so this is known as recurrence in random walk. How recurrent is the random walk? And that means if it starts a position, it starts kind of randomly moving, how long does it on average take to come back to where it initially started? And so what we could do here is we could just do like I is equal to 0, and then we can do like a while true here. And then each time we're going to say, let's come back up here, and we can say if p of x is equal to 0 and p of y is equal to 0, we're going to break. Let me set here I is equal to I plus 1, because we're going to increment it, and then we can just print I here. And this is kind of similar to your last problem. And so I run it, and I have, old C programmer, and that's a C thing you can do. So I is equal to I plus 1. So I run it, and I see on average 22 steps for it to come back. Obviously if I run it again, it's going to take 1300, right? It's a random number. Here it's 4, which basically means going 1, 2, 3, 4. I run it again. It's 4. I run it again. It's 271. And you can imagine doing this a bunch of times and determining what the average is, and so you could start getting statistics for it. So a little bit of overview of Monte Carlo. Obviously, I've given you more complicated problems in your homework. Problem in 3 and 4, what you probably want to do is construct an array and track the positions of the individual particles and do different kinds of checks. Not much different than this, but this is kind of basically what your core code would look like. These statements, or if you have bounding boxes, The other way you could do it is if you have a particle that goes outside the box, you can break out and then start over and drop a new particle in for, again, with the diffusion limited aggregation problems. There's a lot cleaner ways to write this code. This is probably not the cleanest. It's probably a little bit not fast, but it's fairly explicit. And so I would suggest writing it out with if-then statements or if-elif statements, because that'll be easier for you to formulate the process. And start easy, right? And it's often helpful to kind of plot your solutions as you go. As always, if you have questions, please post them in the comment section or put them on Piazza. And thank you.